Hey guys, how's it going? Today we are going to be talking about vectors! Yay! And today in particular we're going to be talking about vector addition and subtraction. We'll call it all vector addition, but that is what we are going to be talking about today. I know you guys are like, I've already learned about vectors, but we haven't talked about vector addition yet, so this is going to be awesome. You remember that a scalar is a quantity with a, whoa, hang on, let me get my color changed up here. It's a quantity with a number or a size only. But a vector is a quantity with a number, a size, and magnitude. All of these things are saying the same thing. Number, size, magnitude. It has a number and direction. So examples of scalars are things like distance, or speed, or mass. All of these things just have numbers. They don't also have directions. Examples of vectors include things like velocity or displacement. These are all things that have both a number and a direction. So in physics, a lot of times we use arrows. We use arrows to represent vectors. And the reason why we use arrows is because they can represent both a size and a direction. So we use the length of the arrow to represent the size, that's the number or the magnitude of the vector, and the arrow points in the direction of the vector quantity. So let's take one of these vectors that we know and love so well, which is velocity. We'll use a lot of velocity when we're talking about vectors, but so if I were to make a vector that looks something like this, here's an arrow. We'll say that's going 5 meters per second north. That's my velocity. And then let's say I wanted to represent a different vector, and this one is about 12 meters per second going east. So you can tell that the length of the vector represents how big it is. So the one that's 12 is a lot longer, the one that's 5 is a lot shorter, and the direction points in the direction that the vector is going. So this one's pointing up because it's going north. This one's pointing to the right because it's going east. So we can actually take these vectors that are going in different directions and add them together. And our answer when we add these vectors together is called the resultant. Now we have 3 different methods for adding these things together, and I'm going to go over these briefly because then we're going to do example problems, and that's really going to show you what's going on. But if the vectors are lined up, then we can add them or subtract them just like in basic arithmetic. Our second option is if the vectors are at right angles, like this, then we can use the Pythagorean theorem. And then this says a clock diagram should be used to estimate the resultant. We'll go over that. And then we're going to use a parallelogram diagram to estimate if the vectors are not at the right angles. So that is basically what we are going to do. Let's start with some examples. So first we're going to start by trying method A. We're going to start by looking at method A when we would use method A, which says if the vectors are lined up, then you can just add or subtract them. So let's take an example. Let's look at some distances because let's look at some displacements. We're going to look at some displacements and see what our net displacement is. So here is one displacement, and here is a second displacement. So this first displacement is about 5 meters. That's our displacement. It's about 5 meters east. And this other displacement here is about 3 meters east. Now when they're lined up like this, see how they're going in the perfectly same direction? All you have to do for these is just add them up. It's super easy. So you can do 5 meters east plus 3 meters east equals 8 meters east. Bam, just like that, you're done. Easy money. So the next one, let's look if we have to subtract these. So we're going to look at forces. Forces are also a vector. It's not a vector we've talked about yet, but it's not too hard for you to understand, and we're going to be talking about forces a lot, so let's get on it. So let's say that I have a box here, and I'm going to have a force. One force is going to be pushing up on this box, and one force is going to be pushing down on this box. Pushing down on this box is 200 newtons down. pushing up on this box is going to be 530 newtons up. So this is a very, very simple problem. We can do 530 newtons up plus 200 newtons down. Now the problem with this is that we have one that's going up and one that's going down. So we fix this problem very simply. We say, well, this is 530 newtons up, and then we're going to subtract this 200 newtons up. Because does it make sense to you that 200 newtons down is the same as negative 200 newtons up? Because 200 newtons would then be going in the negative direction if we decide that the positive direction is up. So if the positive direction is up, that means the negative direction is down. So you can just do 530 newtons minus 200 newtons, and that should give you 330. Whoa, 330 newtons up. Yay! Okay, so that is using method A. Let's do a few more with method A. We're going to look at this airplane. This airplane can fly 100 kilometers per hour with no wind, but we're going to find the resultant velocity if there's a 20 kilometer per hour tailwind and a 30 kilometer per hour headwind. So let's draw a quick picture of this little airplane. There it is. So it can go 100 kilometers per hour forward. We're going to say that this is east with no wind. But then if it's having a 20 kilometer per hour tailwind, that means that something is pushing back on it at 20 kilometers per hour west. Oh wait, no. Just kidding. Jokes. Ah, I erased the whole airplane. Come back. Okay. This is a tailwind. A tailwind's pushing forward. Guys, I'm so sorry. Please forgive me and be gracious with me. Okay, so this is going to be going 20 kilometers per hour east. So when we have 20 kilometers per hour east and 100 kilometers per hour east, we can just add them together. 20 and 100 gives us 120 kilometers per hour east. Yay! Then let's look at this next problem. This next problem is the opposite. It's the one I was trying to do before. So, you guys can tell I'm an amazing artist. So this airplane is going 100 kilometers per hour east, but then it's experiencing a headwind. That is 30 kilometers per hour west. So to do this, we can just say, well, we're going to have east be the positive direction and west is going to be the negative direction. So we can just do 100 minus 30, and that will give us 70 kilometers per hour in the positive direction, which is east. And you can tell that the airplane is still winning against the wind because it's still going east. It has a positive velocity, so it is still continuing forward. Okay, so those are examples of method A, which is what you do when the vector arrows are lined up. Did you see how in all of those examples the vector arrows were going perfectly parallel to each other? So there was no like angle between them. But when does 1 plus 1 not equal 2? When you add or subtract vectors at an angle. If they are not perfectly parallel, like this, or like this, or like this, if they're not perfectly parallel, then they do not add up to equal 2. 1 plus 1 does not equal 2. So let's look at this example. What is the resultant velocity of that same airplane above if there was a 40 kilometer per hour crosswind? Well, let's find out, good friends. So we're going to start by drawing our airplane again. Okay, there's our airplane. It's going 100 kilometers per hour east. But then let's say it's experiencing a crosswind. So something is pushing down on this airplane, and it's pushing down on the airplane with a great strength of 40 kilometers per hour south. 40 kilometers per hour south. So then what you're going to do is you're just going to draw a nice little line like this between them. See, they're at a right angle. You can see right here, this is a right angle here. So we can use this method, we can use this method B because they are at a right angle. So we can use the Pythagorean theorem. And this is super easy. Hopefully you know this from trigonometry. Or from geometry class, or wherever you learn about these things. So you can do 100 kilometers per hour east squared plus 40 kilometers per hour south squared, and that will give you c squared. This is a squared plus b squared equals c squared. So now all we have to do is plug this into our calculators really fast. This should be like 10,000 plus 40,000, this is equals c squared, and then we have to take the square root of that, which you all should do, and it should come out to be, I think if I'm right, and I could be wrong, but about 108-ish. Yes, hopefully that's right. About 108. Oh no, not meters per second. Oh my gosh, pay attention to your units, people. Kilometers per hour. So this resultant vector right here is going to be going some amount of kilometers per hour. Now, if we're talking about which direction it's going in, we can use a clock diagram. So here's how we're going to do it. Are you guys ready? We take these two vectors. One is going like this, and one is going like this. And now we put their tails up against each other. So this is called the tail, and this is called the head of an arrow. So this is the tail, this is the head. We put their tails together, and then we imagine, I always imagine this kind of like a slingshot. Like if I pulled on this arrow, and if I pulled on this arrow, and let's say that there was like a little ball here, and this was a slingshot, like which way would the ball go? Maybe that's not helpful to you. Maybe that just made no sense whatsoever, and you guys are super confused. But the point is, then we could see which way would this get launched, and it would get launched something like this. Don't you agree? Something like this, because it would have a lot of this and a little bit of this, and it would launch off that way. So that gives you a pretty good estimate of both your direction and your size too. So that's how you do that kind of problem. Let's do another one really quick. I want you guys to do this one by yourself. So in this one, you're going to have a displacement. We're going to have two displacements. Let's say you walk this far and you walk 5 meters, and then you walk this far and you walk 4 meters. What is your resultant? So go ahead and do take a quick second and do that math really fast. So you should have gotten something around 6.4 meters. So now I want you to go ahead and do a quick clock diagram where you put the two tails together and find the resultant one and see if that matches up and if that gives you your direction. Okay, so if this is my 5 meters, and we can call this south here, and this is my 4 meters going east, then my resultant is going to be somewhere in between south and east, a little bit closer to south than it's going to be to east because south is a little bit longer than east is, and it's going to look something like that. It's going to be a little bit longer than both of them. So this kind of checks out that we have 6.4 meters, and it's going to be somewhere in between south and east. Okay, so next up, we are going to use this final method. We are going to use a parallelogram diagram to estimate if the vectors are not at right angles. So far we've looked at if the vectors are lined up, we can just add or subtract them. If the vectors are at right angles to each other, like this, then we can use the Pythagorean theorem, and we can use a clock diagram to kind of estimate the resultant. And then finally, if the vectors are not at right angles, in this class we're not going to calculate that numerically. You could use advanced trigonometry, but we won't. But you could calculate that numerically, adding those two vectors together, but we're just going to use something called the parallelogram method. Okay, so let's do this. We're going to use the parallelogram. Is that how you spell that? I feel like it's definitely not. 1 second. Parallelogram. This is why I do physics and not spelling. Parallelogram method for vectors that are not at right angles. So let's try that out. So first, I'm going to have a velocity that is going to be, this is going to be 7 meters per second going this way. Then I'm going to try another velocity, and this one's going to be 3 meters per second. It's going to be my other velocity. So if I wanted to add these together, Well, one thing to start out with is a lot of times these won't be perfectly put together for you. So it'll just be like, here's a 3, and over yonder is a 7. Figure it out. But whenever you use the parallelogram method, you are going to put tail next to tail. So these two tails are going to go together right here. See how these two tails are attached to each other? And then what we're going to do is you're just going to draw some parallel lines. So, because it's a parallelogram. Wow, cool when words make sense. Okay, so you're going to draw a parallel line to this third one. See how I'm going at I'm supposed to be going at the same angle as that one. And then I'm going to draw a parallel line to this vector right here. Parallel line, parallel line. Yes, amazing. And so then what you're going to do, see how I've made a parallelogram now? See this shape right here that's just beautiful? My resultant is going to be from where the tails meet to the top corner of my parallelogram. And that's going to be how I estimate when this angle right here between the two tails is not 90 degrees. So right here it's less than 90 degrees. If I wanted to do it again when they are greater than 90 degrees, we could absolutely do that. So let's say that we have this vector right here and this vector right here. So this one is about 19. And it's going to be meters per second squared, because this is going to be an acceleration. Again, all of these are vectors, and acceleration is a vector. So this is going to be about 19, and this one right here is going to be about 12 meters per second squared. So now I can do the parallelogram diagram the same way. Again, make sure your tails are lined up, or this isn't going to work for you very well. So first I just draw a parallel line, so let's draw a line that's parallel to this one, to the 12 meters per second one, like this. And then let's draw one that's parallel to this 19 meters per second line. It goes like this. Oh, so beautiful. Wow, we made a parallelogram. And then you're just going to draw a nice, beautiful line from where those two meet, right here, up to that top corner. Just like that. Yay! And that's how you can estimate your resultant. So in this first one that we looked at, when you add 3 and 7 together and they're at a really small angle, do you see how your resultant vector is going to be longer than both of them? So doesn't this one looks kind of like, it looks like 9-ish to me. When I'm looking at this one looks pretty close to 12, but I think it's going to be a little less. When you have an angle that's greater than 90 degrees, this angle right here between their two tails is greater than 90 degrees. When you have an angle that's greater than 90 degrees, your resultant vector is going to be a little bit smaller. This is a good general rule. So this looks to me like it's going to be like 10-ish or 11-ish. So that is a good general rule to keep in mind when you are estimating how to add vectors together, the resultant of two vectors for things that are not at a right angle. So that pretty much sums up all 3 of these methods. We used when vectors are lined up, we can just add them. When vectors are at right angles, we can use the Pythagorean theorem. And when vectors are not at right angles, we can use a parallelogram diagram to estimate. So that's pretty much all I have for you guys today, and I will see you soon.